Newton says gravity is a physical force pulling on that satellite. But Einstein says, gravity isn't a physical force at all. It's just an artifact of Earth curving the space-time around it. And that satellite, it's moving straight through that curved space-time. But my question is, why? Why did Einstein and humanity conclude that? I mean, it's cool to repeat quotes like matter tells spacetime how to curve and spacetime tells matter how to move. But science is not about understanding facts. It's about sharpening our thinking. So my question was, how can I intuitively go from Newton's model to Einstein's idea of curved spacetime? What is the exact step-by-step thought process? And I think I finally understand it, and I'm super excited to share that with you. So in this video, we're going to start by pretending we don't know anything about space-time curvature. And by the end of it, hopefully we would have rediscovered all of it intuitively. So if you're ready for this, let's begin. We've had theories for why things fall down for thousands of years. For example, Aristotle believed everything naturally tends to move towards the center of the universe, which is obviously the Earth. Meanwhile, Brahmagupta in ancient India used the term Gurutvakarsanam, a Sanskrit word meaning attraction due to heaviness. That's pretty cool if you ask me. So these ideas were pretty impressive for their time, but they were still pretty vague and local. For a long time, we believed the laws of the earth were completely separate from those that govern the heavens. But starting in the 1500s, all of that changed very quickly. Copernicus helped replace the earth with the sun at the center. Galileo made breakthroughs in inertia and motion. And Kepler uncovered stunningly accurate features of planetary orbits. For example, that they were ellipses, not perfect circles. At the time, these were all disconnected thoughts. They had no broader significance. That is until a young man stuck at home because of a plague decided to do something about it. In 1665, one of the deadliest plagues swept through London, killing up to 100,000 people, nearly 15 to 20% of the city's population. As a precaution, Cambridge decided to shut down, sending students home and halting their studies. One of those students was a young man named Isaac Newton. For the next couple of years, Newton was pretty much stuck at home. But free from exams and lectures, he could pursue whatever he wanted. And so he did. And what followed is arguably one of the most creative bursts in scientific history. Historians call it Newton's Annus Mirabilis, his years of wonder. During this time, he laid the foundations of calculus, showed that white light was made of rainbow, and most importantly for our story, he began connecting Galileo's earthly insights with Kepler's heavenly ones. Years later, this would lead to his universal theory of gravity published in the legendary Principia. And here's that book, Principia. Okay, actually it's a copy of it, translated in English. But if we go to volume 3, here you can see that he proposes that the planets experience a force towards the sun that drops as 1 over r square. I find it fascinating because this is the copy of the original text that for the very first time wrote it down in the history. Oh my god, that's amazing, right? Anyways, and over here you can see he proposes that that force must be proportional to their masses. In other words, the law of gravity we all learned in school. And this was radical because for the very first time, we had a single unified rule, a rule that can be applied both to the earth and the heavens. It didn't just explain orbits or how things fell, but also the tides, predicted the return of Halley's Comet, and a couple of centuries later even helped discover a brand new planet, Neptune, purely from the math. But it didn't stop there. As our instruments got sharper and sharper, our cosmic reach got deeper and deeper, and Newton's laws passed every single test, from binary stars to galaxies themselves. Every observation just kept confirming Newton's law of gravity. That is until a young man who had already shattered the old ideas of space and time started doing some experiments in his head. That man was Albert Einstein. At first, he found some cracks in the universal law, but as he went deeper, the whole framework shattered. But Einstein, why? What made you look at one of the most successful unified model of the universe with so much observational evidence and then say, nope, Newton must be wrong, Gravity is not really a force. It's just a manifestation of four-dimensional space-time curvature. I mean, that's inconceivable. And Einstein says, Mahesh, it's kind of like solving a puzzle, one piece at a time, only to eventually realize you've actually learned backend coding, like on boot.dev, the sponsor of this video. If you go to its homepage, boot.dev claims to be the most captivating, most addictive way to learn backend programming. So obviously I was a little intrigued and decided to check it out. And what I found was, unlike traditional courses, there was no long lectures or theories. You just read a short instruction and you start coding immediately. And I think it's honestly amazing for learning because it's hands-on, interactive, and you get immediate feedback. It checks all my boxes for what makes a good curriculum. And the way the lessons are built, they teach one small thing at a time and slowly build up. I love that. And of course, if you get stuck, there's this AI chatbot called Boots who will nudge you in the right direction. And bonus, the whole thing is gamified. You earn experience points, level up, and unlock achievements. But wait a second, why learn backend development in the first place, you ask? Well, because you can make serious money. Top backend developers earn over $150K annually. And I think that's why Boot puts so much thought into helping you build that skill. But if you don't believe me, don't take my word for it. You can get started for free just by following this link. The link is also in the description. And if you do eventually decide to get the full access, then you can use my code FloatHeadPhysics to get 25% off on your first payment. Okay? Happy coding. Back to the video. In 1905, Einstein published a series of papers that would redefine physics forever. It was Einstein's Annus Mirabilis. One of those led to special relativity. It replaced Newton's old ideas of space and time and predicted that mass is just confined energy, which led the groundwork for particle accelerators, helped understand how stars shine, and helped humanity harness nuclear power. But there was a problem. Special relativity and Newton's law of gravity were incompatible. But why? Well, Einstein says, according to special relativity, no information can travel faster than light. But Newton's gravity is instantaneous. So if the sun were to disappear, then the gravitational force on Earth would instantly be zero and it would immediately feel the change. This violates special relativity. Okay, Einstein, but can't we just modify Newton's laws to fit special relativity? And Einstein says he thought that too until he had the happiest thought of his life, imagining a man falling to his death. Why, Einstein? Why is that the happiest thought of your life? And Einstein says, Mahesh, consider this. When you're in an airplane and that airplane is taking off, it accelerates forward. You feel pressed backwards, right? Similarly, when you're in a car taking a turn, you accelerate inwards, but you get thrown outwards, which means every time you accelerate in a particular direction, you feel a jolt in the opposite direction, right? And I'm like, yeah, that makes sense. Okay, now he asks, Mahesh, but what about when you're falling? Because when you're falling, according to Newton, you are accelerating down at 9.8 meters per second square. But Mahesh, do you feel it? Like in the other cases, even here, do you feel a jolt in the opposite direction? I remember skydiving a few years ago in Switzerland. It was honestly pretty amazing experience. But when I jumped, the moment I jumped from the plane, I felt nothing. No jolts. Totally weightless for a few seconds until the air started pushing. And by the way, this is also the reason why I puked later on because of the zero G. But the point is, no, Einstein, I didn't feel a jolt, so I don't think you feel a jolt when you're falling. And Einstein asks, why not? I mean, you are accelerating down, so why don't you feel an opposite jolt like we feel in the other cases? And I'm like, wait, I know the answer to this. If you go back to the airplane, for example, the seat pushes and accelerates my body first. But my head wants to stay in place due to inertia. Remember, a head at rest tends to stay at rest until my neck pulls it along. So there is a lag, and that's why I feel a backward jolt. And the same thing happens with the car. When I take a turn, the friction between my butt and the seat pulls my lower body first towards the center, but my head tends to move in the straight line because of its inertia until my neck starts pulling along with it. And that's why, again, because of that lag, I feel an outward push, an outward jolt. And fun fact, this is the reason why F1 drivers have enormous neck muscles. They need it to withstand huge turning forces. But coming back to the point, Einstein, gravity is different. While I'm falling, if I were to drop an apple, that apple would fall along with me because gravity accelerates every single thing at the same rate, regardless of its mass. Close to Earth, that is about 9.8 meters per second square. So when I'm falling, every single part of my body is accelerated at the exact same time and the same rate, 9.8 meters per second square. That's why there is no lag, Einstein. And that's why I don't feel an opposite jolt. And that's why I feel weightless. But the acceleration is there. Come on, Einstein. This is high school stuff. But then Einstein asks Mahesh, why does the force of gravity accelerate everything at the same rate, regardless of its mass or material or anything? And I'm like, because of Newton's second law. The net force acting on my body while I'm falling is the force of gravity. And that equals, according to Newton's second law, mass times my acceleration. So look, my mass cancels out, and as a result, the acceleration due to gravity is independent of the mass of the falling body. And Einstein says, this is the crux of the problem, Mahesh. This mass, let's call it your gravitational charge, because it decides how much gravity you feel. And this mass, let's call it your inertial mass, because it decides how much inertia you have, how much you resist acceleration. These two are completely independent and different quantities altogether. And yet, for some reason, they happen to be the same. Why? That's not how other forces work. For example, how much electric force you feel depends upon how much charge you have, which is very different from your inertia. How much magnetic force you feel depends on something called your spin. Again, very different from inertia. And that's how, all other forces are. For every other force, there's a different kind of charge that decides how much force you feel. And yet for gravity, that charge, gravitational charge, just happens to be your inertial mass. Why? Isn't that a little suspicious? And I'm like, wow, Einstein. They say that science is about asking the right questions, and this is at its best. And this is why I love to understand the thinking process rather than the facts themselves. So this is amazing. Anyways, Einstein is still waiting for an answer. And so I'm like, maybe that's just how it is. Maybe there is no deeper explanation for that. And Einstein says, Mahesh, let's find a deeper explanation for that. Okay, what do we know so far? When you're falling, you don't feel your acceleration. In fact, if you were to close your eyes, you wouldn't know if you're falling on Earth or you are in some deep intergalactic space just floating over there. And if you had an accelerometer with you, it wouldn't even detect any acceleration. Okay. Now, instead of coming up with some convoluted explanation like your gravitational charge just happens to be the same as inertial mass, and that's why you don't feel it, but it's there, why don't we come up with the most straightforward answer? If you don't feel your acceleration and you can't detect it, maybe it's not there. Which means maybe when you're falling, you're not accelerating at all. And I'm like, hello, there's gravitational force pulling on me. And Einstein said, okay, maybe there is no force of gravity. And I'm like, wait, there is no force of gravity acting on me. I'm just floating there. Then why do I hit the ground? And Einstein's like, maybe you don't hit the ground. Maybe it's the ground that's accelerating up at 9.8 meters per second square and it hits you. At first, I'm like, come on, Einstein, that's crazy. And Einstein says, maybe so, but it answers our nagging question. Because it's the ground that's really accelerating up at 9.8 meters per second square, from the point of view of the ground, someone standing on the ground, it gives you the illusion that gravity accelerates everything down at 9.8 meters per second square. Isn't that a much simpler explanation, Mahesh? So this is where the whole gravity must be an illusion, perspective comes from. And this reminds me of something called the Occam's razor, which says often when you're trying to solve a problem, the simplest explanation is the best. And again, you can see that's what Einstein is doing over here. But wait a second, Einstein. If there is no such thing as gravity, it's all an illusion, why am I feeling my weight right now? Because Mahesh, the ground and the chair that you're sitting on right now, that's accelerating you up at 9.8 meters per second square. And just like in the airplane, when you were accelerated forward, you felt an opposite jolt due to the lag and inertia. Right now, because you're being accelerated up due to your inertia, you're feeling a downward jolt. And that downward jolt is what makes you feel like you have weight. There is no real force of gravity. What you feel as gravity is just inertia. And this is why the gravitational charge in the Newton's formula of gravity just happens to be your inertial mass. Because there was no gravity. What you've been feeling all along is just your inertia. It's no different than the opposite jolt you feel when your airplane is taking off. It's the same thing. It's just that the jolt is downwards, and that makes you feel like you have weight. That is insane. That is crazy. So just to be clear, Newton says the ground is inertial, not accelerating, and it's the falling things that are accelerating. But Einstein says, nope, it's the falling things that are inertial, not accelerating. It's the ground that's accelerating upwards, making everything stick to the ground. But wait a second, both models seem plausible. How do we know who's right? Well, we need an experiment to tell them apart, and there isn't any. So both points of view are equally valid. And therefore, Einstein calls it the equivalence principle. So his big claim is that being in an accelerated frame is indistinguishable from being in a gravitational field. This seems to be an extension to Galileo's relativity. Galileo figured out that rest and constant velocity motions are the same thing, looked from different points of view. Now, Einstein takes it to the next step and says, maybe acceleration and gravity are also the same thing, just two different points of view. So he's trying to generalize things. But hang on, Einstein, your equivalence principle has a big problem. First of all, Earth is round. So if the ground is accelerating up in all the directions, shouldn't the Earth be expanding? But there's another issue. Falling things also stretch and squeeze. It's just that for small things, we don't notice it. But if there was something huge like an asteroid hurling towards the Earth, it would stretch significantly. Sometimes it can even tear the asteroid apart. And it's not just the asteroids. Even the Earth and Moon fall towards each other, and they're pretty big, so they too significantly stretch and squeeze. And on Earth, this effect is what gives rise to tides. That's why we call this effect the tidal effect. Newton's model, where you consider gravity as a physical force, can explain this beautifully. Gravity gets stronger closer to the Earth. So if you've got a big object like an asteroid, this part feels slightly stronger pull compared to this one. So this part accelerates more than the part behind, and look, that's what stretches the asteroid. And the math works out, and it nails the explanation for tides. But Einstein, you say there is no such thing as gravitational force. According to you, this asteroid is just floating. Absolutely no force is acting on any parts of it. No accelerations at all. So how do you explain the stretching? You can't explain the tidal forces, buddy. Your equivalence principle breaks. What you got to say about that? And Einstein says, yeah, Mahesh, you're right. This means that the equivalence principle is only valid locally, in small regions where gravity can be assumed to be uniform. But in large regions where the gravitational field varies, it cannot explain the tidal effects. And so I struggled with this problem for nearly 5 years, but then I had a breakthrough. I found a way to explain how an asteroid can stretch even without any forces acting on it. How? How is that even possible, Einstein? And Einstein says, Mahesh, first, let's bring this problem into my territory. Let's draw a space-time diagram for that. Now, a quick refresher. If a small rock is at rest in space, it's still moving in time. So its graph is straight and vertical. We call this the rock's whirl line. If the rock's moving at a constant velocity, it's still straight, but tilted. So look, inertial motion always give you straight whirl lines. But if the rock accelerates, that whirl line curves. More the acceleration, more curved the whirl lines. So remember, in space-time, straight whirl lines are inertial, non-accelerating, and curved whirl lines are accelerating. Okay, now according to Newton, we can consider the ground to be inertial. Let's assume it to be at rest. And the falling person is accelerating towards the ground, so their world line curves. But in Einstein's model, the falling person is inertial, say at rest. So their world line is straight, and it's the ground that's accelerating up. So far, so good. But what if a big asteroid is falling? In Newton's model, the front of the asteroid being closer feels stronger gravity. So its world line curves more than the back. That's why it stretches. This is the tidal force. And this is a fact. So the same thing must happen in Einstein's model as well. Somehow these points on the asteroid must also move farther apart. But wait, Einstein, according to you, that asteroid is inertial. There are no forces acting on it, which means I can assume that all the parts of that asteroid are at rest. So the world lines of these 2 points should be vertical and parallel. There should be no curves, no acceleration. And yet, somehow the asteroid should stretch, meaning the distance between these vertical parallel lines should increase. How can the distance between parallel lines, straight lines, increase without curving? That's impossible, Einstein. And Einstein says, Mahesh, that's not the attitude we have over here. Don't say it's impossible. If you want to have breakthroughs, instead ask, how can I make this possible? And I'm like, okay, how can we make parallel straight lines move farther apart without curving them? How can we make that possible? And Einstein says, what if we drew them on a globe? Imagine 2 people walking north from the equator along the lines of longitude. They start off parallel and they're walking as straight as possible. No turning, no curving. And yet they slowly move closer together. Why? Because the surface itself is curved. On curved surfaces, look, straight paths can come closer. Now, if the surface was like a saddle, then the straight parallel paths could also drift apart. And I'm like, wait. These are not straight lines, Einstein. These are curves. I mean, the line of longitude is a part of a circle. So this doesn't apply over here, right? And Einstein asks, Mahesh, what's your definition of a straight line? And I'm like, well, it's the shortest path between 2 points. And Einstein says, well, a line of longitude is a shortest path between, say, the 2 poles of the Earth. So it fits the definition of straight line. Now, to avoid this confusion with this whole straight terminology, the shortest path between any 2 points is in general called a geodesic. Okay? So, long story short, on a flat piece of paper, if you draw 2 parallel geodesics, they will have to stay equidistant. But on a curved surface, parallel geodesics can converge or diverge or do whatever they want. So coming back, every tiny part of this asteroid, including these front and back pieces, are inertial, right? If we assume it to be at rest, then their paths through spacetime must be straight, geodesic, and parallel, right? Now, we know the asteroid stretches. So I want these paths to move away, but still stay a geodesic. There is only one way that can happen. If the underlying spacetime itself is curved, then, like on a saddle, parallel geodesics can diverge. This is how we can explain the asteroid stretching even though there are no external forces acting on it. It stretches because even though there are no forces, these inertial world lines are on a curved spacetime drifting apart, making the asteroid stretch. This is how Einstein concludes by analyzing the tidal forces that our spacetime must be curved. Isn't that amazing? I mean, oh my God, this is how it happens. Einstein, this is amazing. But I still want to circle back to the question that I asked earlier. If the ground is accelerating up, shouldn't the Earth expand over time? And Einstein says, all right, let's draw a spacetime diagram one more time. Without any mass, spacetime is flat. That means 2 parallel geodesics, like the world lines of these 2 apples at rest, for example, will stay parallel. So the distance between them stays constant. What happens when we add the Earth? Now, in Newton's model, space-time still stays flat. The Earth pulls on the apples, curving their whirl lines inward. So look, the apples deviate from their straight inertial paths. They accelerate. That's gravity as a force. But in Einstein's model, there is no force. Instead, the Earth curves space-time itself. So these paddle geodesics don't stay paddle, they converge. The apples are now just following their inertial paths, straight lines in curved space-time. On the diagram, those paths look curved, but they're not accelerating. That curvature is just what straight looks like in curved space-time. Now, zoom out and look at the opposite ends of the Earth, Mahesh. Their geodesics should also curve inwards, because space-time is curved. So if these two pieces of Earth were inertial, they too would move towards the center. But they can't because the Earth's matter below resists it. So it constantly pushes them outwards, accelerating them away from their inertial geodesic. So on the diagram, these whirl lines look straight, but they're accelerating. That straight line is just what an accelerated path looks like, again, when the spacetime itself is curved. So look, Mahesh, in curved spacetime, Earth's surface must be in a constant outward acceleration just to maintain its shape. Otherwise, it would collapse inwards. By the way, it's similar on the globe. If these two now want to maintain a constant distance between them, they have to move away from their geodesics. So look, they have to keep moving away from each other just to maintain their distance. And this kind of makes sense, right? Because the curvature naturally tends to bring them closer. So if they don't want to come closer, they have to move away from each other. Similarly, the ends of the Earth have to be accelerating away from each other, outwards, just to maintain the shape in the curved spacetime. And because of that outward acceleration, people on the Earth feel their weight due to their inertia. So can we now summarize Einstein's thinking process that led him to this whole idea of curved spacetime? First, freely falling objects all accelerate at the same rate, regardless of their mass. He finds that very suspicious. He doesn't accept the whole gravitational charge just happens to be the same as inertial mass. He says, let's keep it simple. Since falling folks don't feel or measure any acceleration, he claims that falling can be treated to be inertial, and gravity is just equivalent to acceleration. And as a result, he concludes that gravity must not be a real force, it's just an illusion. But that doesn't explain why falling objects get stretched. So the next crucial step is he rephrases that problem using geometry. He realizes that asking how can a floating object with no forces on them stretch is the same as asking how can parallel straight lines move away without curving. I find that a stroke of genius because that he rephrased the problem in terms of geometry, a physical problem in terms of geometry. That's amazing if you ask me. And finally, he connects all the dots and realizes on curved surfaces, parallel lines can drift apart without curving themselves. And so the same thing must be happening over here, and that's how he explains the tidal forces by saying space-time itself must be curved. We just rediscovered the step-by-step thinking process that planted the seeds for general relativity. But this is just the tip of the iceberg. I mean, Einstein got stuck again. So let me know if you want to dig deeper. There is so much more to rediscover over here. Stay tuned.